Hey everybody, Dr. Phil here, back with another video on measures of association and how that pertains to the world of research. So let's jump right in. So the first thing I wanted to talk about was measures of association with respect to interval and ratio data. There's a lot of different ways to measure association, correlation, association. For interval and ratio, the Pearson product moment correlation coefficient is probably the most common. And that's for continuous linearly related variables. So think about linear like a line. Doesn't have to be that, it could be like that. It just has to be a line. Interval and ratio, the correlation ratio eta is typical. This is for nonlinear data or relating a main effect to a continuous dependent variable. For interval and ratio, typically you would use biserial. This is for one continuous and one dichotomous variable with an underlying normal distribution. For interval and ratio, a partial correlation. This is three variables relating two with a thirds effect taken out. The interval and ratio, we could use multiple correlation with three variables, again relating one variable with two others. And then interval and ratio, a bivariate linear regression, we're predicting one variable from another's scores. Measures of association for ordinal data. We can use gamma, which is based on concordant and discordant pairs, basically P minus Q. And we're looking at the proportional reduction in error interpretation. We call that the abbreviated the PRE interpretation. Kendall's tau, which is again P minus Q based, so it's sort of difference based. And we make an adjustment for tied ranks. Kendall's tau. The first one I should say is Kendall's tau B. This is Kendall's tau C. Again, P minus Q difference based with an adjustment for table dimensions. Summers D, again, P minus Q based with asymmetrical extension of gamma. And then Spearman's rho, product moment correlation for ranked data. So just some examples of the measures of association for ordinal data. For nominal data, we can use phi, which is like a chi-square based for 2 times 2 tables. We can use Cramer's V, which again, chi-square based with an adjustment when one table dimension is greater than 2. We could use a contingency coefficient C, which again, chi-square based with flexible data and distribution assumptions. Lambda, again, that's a PRE based interpretation. Goodman and Kruskal's tau is also PRE based with table marginals emphasis. Uncertainty coefficients can be useful. That's useful for multi-dimensional tables. And then a kappa is sort of a measure of agreement, if you will. So Pearson's product moment correlation R. This is a very popular one. So is there a relationship between X and Y is sort of like the basic question. What is the magnitude of the relationship? And also what is the direction of the relationship? So the magnitude is sort of like how strong that association is and that relationship is, and then the direction is it positive or is it negative? So here we see some scatter plots of correlations between two variables. So if we look at this one says R is -1. This is what's called a perfect negative relationship. And this is obviously R equals 0. There's no relationship there. R equals +1. This is a perfect positive relationship. Again, I've never seen a perfect negative or positive in my career. If you see, notice here like R equals -9 and then R equals +9, then these are very strong. And by the way, -1 is like I say, it's perfect. That's the strongest it can get. It's a negative relationship, and then +1 is the perfect positive relationship. Again, like unlikely to see these. And then these are very strong. If you got like an R of negative 0.9 or positive 0.9, that would be in the world of research that would be pretty strong. And then here we have, R of plus and minus 0.4. So again, you can kind of see that it's like this one's trending down, this one's trending up. Um, it's a pretty loose association, but if you kind of study it, you can tell that that's the case. And here we can see some scatter plots for the same kind of summary statistics. Again, we're basically just looking at how close are the plots to the line. So here we see that, well, by the way, we're looking at the vertical distance between the point and the line to really get an idea as to how strong the association is. So this one's a pretty good association. This one's reasonably good. This one's very good. This one really not so much because you notice that, the line is sort of, going from sort of the bottom left-ish to towards the top right, and then you notice all the points appear to just be, except for there's maybe one or two outliers at the very top right here. They're all just sort of, seem to be arrayed in a vertical line. So this is a plot of Forbes 500 net profits with cash flow. So we would sort of assume that, greater cash flow would equal net profits. So we would kind of expect there to be a sort of upwards line. And you can, again, we didn't do a line of best fit here, but, if you looked at that, your brain is probably like, yeah, I can see that there's a kind of a pattern here from bottom left to top right. So a diagram of common variance. So this is sort of like, how much overlap do we have here? So we have an R of 0.93. So basically we have a 0.93 association. That, by the way, is would be considered a very strong association. And then the R squared. So the R squared is what we call the coefficient of determination. Just basically how much of the movement of one variable explains the movement of the other variable. And I can tell you, firsthand, getting anything like an R of 0.93 and an R squared of 0.86 would be very impressive in the world of research. So the interpretation of correlation. So, X causes Y causes X and Y are activated by one or more other variables. That's typically the case. It's very rare, really, in the world that, just one thing causes something else, right? Um, a lot of things typically, varying associations, typically cause something to be what it is. X and Y influence each other reciprocally. That's possibly the case as well. One word of kind of caution here, I would be careful about using the word causes because that's something that, research we really tend to stay away from. We tend to shy away from that. We tend to use, words like when I'm writing a research paper, when I was writing my PhD dissertation, then I would write things like is associated with, right? Is correlated with. I was certainly told um, by my supervisor amongst others that you should the case that you can actually say something causes something else are very few and far between. So a coefficient is not remarkable simply because it's statistically significant. And actually, you mentioned this in another video. It's got to be practically meaningful, right? So I think sometimes in the kind of world of research in the ivory towers at some universities, these researchers get so down into the weeds in, they find something that's yeah, it's statistically significant. It is a finding, but it has literally no or very little practical relevance whatsoever. So the one of the goals of research is, of course, to hopefully make the world a better place, right? So finding something that's out that might be significant, but it's very obscure, then you would have to question the usefulness of that. And testing goodness of fit. So Y is completely unrelated to X, and no systematic pattern is evident. So that you may run a research, you may commission a research study, and that may be the case. There are constant values of Y for every value of X, and then the data are related but represented by a non-linear function. So think of like the first one as there's no association at all. The middle one is there are constant values of Y for, that's like there's a great or a perfect association. And then the third one is more likely what you would get. The data are related but represented by a non-linear function. So you think about those points we saw in those lines, they weren't, some of those points were, yeah, they were close to the line, but they weren't directly on the line. And then I kind of alluded to this earlier, the coefficient of determination R squared, the total proportion of variance in Y explained by X. So in this case, like, R squared is 80% or more. Yeah, it's, if you can get it, if you can get 80% or more, then that would be great. But, I mean, you can certainly publish papers with, coefficient of determination is less than 80%. Of all the papers I've published, I'm going to say maybe one or two, certainly no more than three, had an R squared of 80% or more. So just know that, what I don't want you to do is read that and think, okay, if I'm going to publish anything, I've got to get the R squared has to be higher than 80%, otherwise no one's going to publish it. And that would not be the case at all. All right, thanks for watching for always, and I will see you in a video very soon. Take care.